Hello class, this is Professor Kamen, and this video presentation is on the properties of metals. In manufacturing and manufacturing processes, they often use metals as their product, so it's very important for us to understand those properties of those metals so it can help us to better understand those manufacturing processes. Let's go ahead and get started. First type of properties we're going to talk about are mechanical properties. These are properties that really talk about how a material will perform under a load. And when we talk about a load, we're talking about when it's stressed or when it's bearing some type of force. So there are different types of stresses or different types of loads that mechanical properties describe. The first one is called a tension or a pulling apart. And you can see that right here. That's when things are being pulled apart. So that's your tensional stress or your tensional load. Another type of load is your compressional stress or compressional load, and that's kind of like a pushing things together or smashing things together. The next one is a shear stress or shear load, which is more of like a cutting or a ripping or a tearing action. And you have another example of that right here, a shear stress, which is like a slicing, like scissors, or cutting or tearing, that type of action. And then the last one is called torsion. And torsion is simply a twisting load or a twisting stress. And so one of the most common types of testing for mechanical properties is called the tensile testing. It is tensile testing. And when you perform tensile testing, you get a curve called the stress strain curve. And it looks like this. And when we test other different types of mechanical properties based on other loads, you get curves somewhat like this as well, based upon whatever load you're testing. But in this case, we're looking at the tensile stress strain curve, which is very, very common for you to do if you want to measure the mechanical properties of a metal. And so what happens here, zoom in here a little bit, is that you're measuring the strain, which is essentially how long it stretches, against the stress that's caused, which is essentially the intensity of force. And at the beginning, you can see you have this long straight line here. That's called the linear elastic region. And that's where your metal is under elastic deformation, which means that if you were to deform it, or in this case, stretch it, since we're talking about tensile stress, then after you stress it and deform it and let it go, it's going to bounce back to its original shape, just like a rubber band. So that's what occurs during this region right here. Now that happens until you get to this yield strength point. And your yield strength point is when your part goes from elastic deformation to plastic deformation. And so now think of having like a plastic part or soft plastic part where when you bend it, it actually stays in that shape. Okay, and so that's called plastic deformation. And that's what occurs at the yield strength point. And coincidentally, this is typically the point that most engineers would use for failure when you're talking about building different types of structures. So after you get to that yield strength point, you can see that you have some deformation here, okay? But it's uniform deformation, all right? And so you can see the stretching, which you can't really see as much on the uniform elastic deformation, but you can see the stretching a lot more, but it's uniform, okay? Now that carries on until you get to that ultimate tensile strength, okay? And take note that even as you start at this yield point, you're actually getting stronger even though your part is deforming. But when it gets to the ultimate tensile strength, that's the strongest it can get. That's where it can maintain or hold the highest amount of stress or intensity of force. And then after that, it kind of falls off into fracture. Now keep in mind that this region in between ultimate tensile strength and the breaking or fracture strength, you have necking occurring, which is same thing as non-uniform plastic deformation right here, and then it finally breaks. And here's a video of a tensile test right here. Let's see if I can turn that up a little bit. Okay, it's being pulled. I don't know if you can see right now, but you can see that it was in elastic deformation. Now it's past that ultimate tensile strength. You can see it start to neck right here, okay? And then it's about to get into breaking or the fracture area. There we go. I'm gonna turn this sound up just a little bit. Oh, it's already up all the way. Okay. Here we go. Okay. Then I'm gonna get back to what we are doing before. All right. Now let's look in a little bit closer in that stress strain curve. So this stress strain curve, they all look somewhat similar depending upon the mechanical properties of your metal, but this has all the same things that I pointed to you before. It has this elastic region right here. And in this elastic region, the slope of this line, by the way, is called the Young's modulus. So that's a property of metal. It's not a mechanical property, which means that it doesn't describe how the part forms when it's being stressed or loaded. But Young's modulus is a physical property that describes how stiff the metal is. So that's what a physical property is, something that describes what is intrinsic to the metal or the product itself. You get to the yield strength, then here's the ultimate tensile strength. Remember, between yield and ultimate strength, you have strain hardening, which means it's getting stronger. And then after ultimate tensile strength, everything just falls off into fracture. And in between that is when necking occurs. So I want to make sure that you understand these definitions. We talked about yield strength, ultimate tensile strength, that elastic limit, which is very similar to the yield strength as well. It's that the highest stress in which that material will elastically deform, right at that point when it's coming over from elastic deformation into plastic deformation. And then we also describe the modulus of elasticity, and that is actually the same as Young's modulus. There's just two different names for the same concept there. And remember, it's a physical property, not a mechanical property that describes the product stiffness, okay? Other mechanical properties are ductility. So ductility is your ability to be pulled into a load. So that's in tension, being pulled into a wire, okay? So that's very important for metals like copper that are always being used as wires. Then you have malleability, which looks at the deformation, but under a different load. So malleability is the ability of a metal to be deformed when it's loaded in compression, okay? So ductility, ability when loaded in tension, and then malleability, ability when loaded in compression, okay, or hammered into a sheet. So that can be important for somebody who maybe is doing forging or sheet metal work or something like that. Now, plasticity is a general term for how easy can this metal be permanently deformed, okay? And then elasticity is another general term for the ability of a metal to perform elastically. That means to be stretched or pulled or twisted or whatever the case, and then to return back to its original shape, right? Now, going from there, I want to ask you a question. That question is, what do you think could affect how plastic or brittle a metal is? And when we talk about plastic or brittle, plasticity, remember, is the ease of it to deform, fail by deforming. Now, brittle means the ease of it to fail by cracking or breaking, okay? So what kind of
iron is malleable at high temperatures. Therefore, it must
characteristic would be able to determine the difference between those two? So this whole video is sort of a hint, so I'm guessing you could probably tell what that hint is right now. That hint is obviously the temperature, right? And so if you raise the temperature or you drop the temperature, it could change and it could determine whether that material is going to act in a brittle manner. That means it's going to break, fracture, or whether that material is going to act in a more ductile manner, which means that it's just going to bend.
Copper and aluminium are malleable at room temperature. Metals can be drawn into rods and wires by heating and pulling apart. Copper can be drawn into the very thin wires used in electric cables.
All right, there are other types of mechanical testing, and I'm not going to show you all these videos here, but I am going to post them into the module so you can see them. These are two types of hardness tests. Hardness is a mechanical property that describes an ability of the ability of a metal to resist indentation. Okay, and I'm just going to play just like the first couple of seconds of that so you can see what I mean.
These are used to select and program different testing methods.
Oops, that video had already started.
Below the control method, the hardness of a turbocharger housing is to be measured.
Okay, so essentially right here, they're just trying to see how hard this turbocharger housing is. And so they're going to take indenter right here. It's typically made out of something extremely hard. Some of them are diamond tipped. And it presses it into the housing, okay, and to see how big of an indentation it makes. So that's how it measures hardness. The Rockwell hardness test is very similar, except it uses a different shape indenter. I think here we have kind of a diamond-shaped indenter. Here we have a round, circular-shaped or a spherical-shaped indenter. And then we have another test called the impact strength test, or the Sharpie impact strength test, and that measures your impact strength, which is also your toughness. Okay, so I'll show these videos, or I'll post these videos to you on your model so you can look at those. Let me skip past those. Now, another characteristic of a metal is its ductile brittle transition temperature. Now, not all metals have these, but a lot of them do. And this is the temperature at which a metal changes from being ductile to brittle. So remember, this is when it's being put underneath the load. So it's important to understand how a metal is going to fail. Is it going to break and crack, or is it going to bend? And that could change how it's going to be used for different situations and different applications. And now you have to think, because if you originally plan a metal to bend or to be ductile, then it's put into a very, very low temperature. It could change from being ductile, okay, since now it's in a low temperature, now it's brittle, okay? And if you think something is going to be brittle and crack, when you put it in a higher temperature, then now it's more ductile now. For some reason I can't speak. And it will bend instead of cracking. Remember, the idea of what's brittle is the characteristic of material that's going to fail. It's going to fail that by fracturing or breaking, okay, instead of bending or deforming. Another mechanical property is called creep. Now, creep is actually very, very interesting. It's when you have continuing plastic flow, and that's at a stress below the yield strength. Now that's important, stress below the yield strength, because I mentioned to you before that most engineers would use this yield strength as a point to determine whether a material has hit failure or not, especially when building structures like buildings and bridges and things like that. And so if you have this mechanical property here and you have something occurring, right, below the yield strength, that's very important, all right? This usually occurs at high temperatures. So when you have when you have high temperatures sustained for a long period of time, what will happen is that part will start to plastically flow, okay? And as it does that, it gets weaker and weaker at the highest stress points, and then it could break. And I can tell you about when I was interning at a power company, we had that happen to some of the tubes in our boiler system. And I don't know if you're familiar about how to make power, but what happened is there were tubes very, very similar to this, okay? And creep was occurring to where the stress was not above the yield strength, but because of creep, okay, things were plastically flowing and it was getting weaker and weaker at a certain point, and then it blew up. And so in a power point, these tubes have steam at extremely high temperatures and pressures. And so when that weak point let go, there were explosions and people died. And so there's this big, huge investigation, all because of creep, and because they did not account for that. This is just another graph. I'm not expecting you to memorize this or anything, describing how creep works. Strain, remember, is how something elongates or stretches, which is what happens with creep. And over time, under sustained temperatures, what will happen is you'll have creep, and then when it gets to a certain point, boom, that creep shoots up, and usually you'll have failure, even though it's underneath the yield strength. Fatigue testing is also another way that a material can fail underneath the yield strength. So what happens with fatigue is that it's all about forces being repeated, so repeated loading. So that could be loading and unloading. That means you put something on, take it off, put it on, take it off, put it on, take it off. Or it could be a complete reversal of loading. So for instance, you could pull it and then push, then pull, then push, then pull, then push. But as long as that does that in a repeated fashion, then fatigue can occur. Just like if you're lifting weights, you're lifting that dumbbell, you do it once, you're fine, you do it twice, you're fine. Then all of a sudden it's harder and harder to do it third and fourth time. Or if you've taken a paper clip and you've bent it once, it's fine, but bend it back and forth 3 times with the same amount of force, then it's going to crack. So that's what fatigue testing is responsible for. And here's a chart that just identifies how you can actually have some metals that, to a point, can be immune to fatigue. Okay, and so here's your stress, which is the amount of forces are on it, and as a stress right here, you have the stress amplitudes. This is right here the number of cycles down at the bottom you undergo. So obviously the number of cycles, the more fatigue you have. And this stress amplitude right here is just the highest amount of stress it could take. And so the longer you go, right, the lower amount of stress you could take. And for some different metals, in particular 1045 steel, there's a point where it bottoms out where no matter how many more cycles or how many more repeat loadings you put on it, it's going to still be able to take that stress. And some metals, they just continue to go down and down and down and down and down and down. Like for instance, this 2014 aluminum. Now we talked a lot about physical properties. About mechanical properties. What about physical properties? The difference between mechanical properties and physical properties I mentioned before is that mechanical properties describe a metal when it's under load. So how is it going to react when it's under load or when it's being stressed? A physical property is a property that's inherent to the metal. Okay, I mentioned modulus of elasticity. That's the metal stiffness or product stiffness. Okay, we have density here. So density is your the ratio between mass and volume. Okay. In other words, how much mass does it have for every unit of volume? And that is a physical property. And here's just an example of different liquids of different densities. They went ahead and they kind of organized themselves out because some are heavier than others. Melting point is another physical property. So what's the temperature at which that metal is going to change from a solid to a liquid? That's the melting point. Okay. Quick question here. What manufacturing process do you think is necessary to know about the melting points of metal? Well, if you've guessed already, then that answer is casting, because in casting process, you melt the metal down, pour it into a mold, and then you let it solidify. Also, I'm not sure if I mentioned thermal conductivity. Okay, so how well does it conduct heat? That is a physical property, as well as electrical conductivity. I don't have a picture for that, but electrical conductivity is also a physical property. Thermal expansion is a physical property. So expansion and contraction. Thermal expansion and contraction occurs when you have metals. If they're in a higher temperature, they tend to expand, and if they're in a lower temperature, they tend to contract. So this can be very important for design, particularly for manufacturing of metals, because if you have a piece of metal that performs some type of function, you're going to have tolerances that take into account this thing right here. Okay. Now this is, I know you're looking at this, you're like, what in the world is that right there? I don't know what that means. It's actually a very simple equation. You just have to see what these little symbols mean. And for some reason, when we like to do equations, we like to use Greek letters. So this is a Greek letter delta, this triangle right here. It means change. So we're saying the change in L is the length. So the change in the length, okay? We're talking about linear expansion and contraction here. But if you look at things in 3D, things can expand and contract in 3 dimensions. We're not going to cover that. We're just looking at in 1 dimension here. Alpha represents your coefficient of thermal expansion. So what your coefficient of thermal expansion is just a lot of smart people got into a lab environment and they calculated or worked out this number here that relates all the different metals and how fast or how slow they expand depending upon the temperature. Then you have this LO. This represents your original length. Okay, so your original length really affects how much your final length is going to be. And after that, you have the delta T. Remember, delta means change in. T stands for the temperature. So what's your difference in your temperature from the beginning to the ending? Okay, from the temperature that you were to the temperature that you are right now, what's the difference? And that's what goes there. So an example of calculating the thermal expansion would be right here. Let's say a 1 times 10 to the 4th meter steel railroad track. So 1 times 10 to the 4th, 1, 2, 3, 4, so that's 10,000. Okay, so 10,000 meter steel railroad track with a coefficient of linear expansion of 12 times 10 to the negative 6, okay, per degree Celsius. So here's our coefficient of linear expansion. Okay, here's our original length. All we need now is the temperatures, and it said the temperature changed from 18 degrees Celsius to 38 degrees Celsius. So there's a 20-degree temperature change. Okay, so if you put that into your equation, and it's all just multiplication right there, you just plug in everything in. Plug in the coefficient of expansion, plug in your original length, plug in the difference of the temperatures. Remember, the difference of the temperatures, you want to do final minus initial. Okay, and once you do that, what should you get? So you should get about 2.4 meters, okay? And so your expansion is fairly small. You have a track that's 10,000 meters and it only expands 2.4 meters. But if you're on a train and all of a sudden there's an extra 2.4 meters of track in the wrong direction or whatever the case, that can make a big difference. So that is another property, linear expansion, linear thermal expansion. So here's a quick video that demonstrates and illustrates how linear thermal expansion works. You can see here right now the ball goes through the little ring with no problem. Okay, back and forth, he went through it. Now what he's doing is he's heating the ball for about 5 minutes. And so this would be his linear expansion right here, since he's heating the ball. And upon heating, of course, the ball expands its diameter. Now it can't go through. Okay, so just a few minutes before the ball was going through, now it can't go through, and that is a product of linear thermal expansion. Now, so it'll cool down enough to kind of fall through there. Now we also need to talk about identification of metals. This is from a very general standpoint, and I chose some very common metals that you would see in a manufacturing environment. All right, we're going to identify these metals by basic characteristics like their appearance. Okay, so the color, the reflectivity, like how shiny it is. Also by the weight, and another is by whether it's magnetic or not magnetic. Okay, these are basic ways in which you can try to hone down and identify what a metal might be. First, let's go ahead and look at carbon steel, which is very ubiquitous. It's used all the time in construction and in manufacturing. And you can see that carbon steel is magnetic. Okay, so anything that has that iron in it is going to be magnetic, and steel has iron in it. Okay, now just depends on how much iron it has in it. But for normal types of carbon steel, it's going to be kind of like a dark grayish color, but and here's one, actually a samurai sword. I thought was pretty cool, but it's going to be a kind of dark grayish color, and you see the weight is about 490 pounds per foot cube, so it's a weight per unit of volume. All right, so this is comparable to other metals such as stainless steel and also other metals such as copper. Okay, but we'll find out in a little bit how aluminum stands up to this. So this is stainless steel. Stainless steel is really known for its abilities to resist corrosion. Okay, and it's also a lot stronger than a normal carbon steel. And so this is like a shiny dark gray color. So still a dark gray, but it's a shiny dark gray, and that's from the chromium that you also find in stainless steel that helps make it corrosion resistant. It is not magnetic, so that's a large difference between stainless steel and also between carbon steel. It is not magnetic. And you can see examples on this watch. You got some bowls here that you'll use in the kitchen. And then right here you have some locking, some locking mechanism. You have bolts. You have, I think they're just about all bolts. Yeah. All right. Aluminum. Okay. Aluminum. You can see here in the pictures has this kind of actually a light gray, so it's a little bit brighter than your carbon steel and also your stainless steel, and it's also shiny too. So it's shiny like the stainless steel is as well. But see here, it's lighter, it's shinier. Okay, and it's not magnetic. So another big difference, not magnetic. One of the things that you'll find with aluminum is that it is a lot lighter rather than all of our other metals that we're looking at. And so all of our other metals hover around between 500, around 500 and 550 pounds per cubic foot. But this particular one is only 168 pounds per cubic foot. So that's almost 2.5 times lighter than all the other metals we've been talking about. And so if you want to determine the difference, say, between aluminum and stainless steel, which I find hard sometimes because they're both gray, they're both shiny. Of course, the stainless steel is a little bit darker shade than the aluminum. But if you just take two relatively same volume pieces, same size pieces in your hand, you can determine the difference in weight. And that's one way that you could identify it. And then, of course, copper is mainly different, of course, by its color, which is kind of like a reddish brown type color. It is also not magnetic, okay? And this weight for copper is about the same as what we've been looking at for carbon steel and also for stainless steel, about 560 pounds per cubic foot. So those are some basic ways in which you can identify or tell the difference between some of the metals that are more popular in manufacturing and manufacturing processes. Now let's talk about non-destructive rather testing. And when we mentioned mechanical properties, we showed you lots of types of mechanical testing. But if you remember, in that mechanical testing, what do we do with the part? We essentially tore it apart. Now, you didn't see the Brinell test and the Sharpie test and all those, but you did see the tensile test. And in the tensile test, we took a test piece, and to get that property, we had to destroy it. And that's the thing about mechanical properties. If you want to measure it, you have to injure or destroy whatever you're measuring. And so we can't do that if we have parts or products that are in service or that are in use. And so that's why we have non-destructive testing, because we can test but not destroy it. All right. Now, there is another big difference between non-destructive testing and mechanical testing, and that's non-destructive testing really doesn't measure your mechanical properties. What it does is it looks at the defects, voids, inclusions, cracks in a metal part to determine if it's close to failure, okay? Which is different from measuring its actual mechanical property, all right? So here are some examples of some of the cracks and voids that you can see. There's cracks here in this piping. Then if we continue to look here, we have some temperature testing going on, and you can see just in this small little area, the temperature spikes up, which is completely different from everything else around it. So that's definitely a sign that something wrong is going there. Then here you have a type called fluorescent dye penetrant testing. I'll talk to you about that in just a little bit. And you can see a crack here that it was very, very difficult to see before. All right, so we're going to talk about several common types of non-destructive testing. Right here, I'm just going to generally take you through the process of them very quickly, and then I have a lot more information on these non-destructive testing methods in your module. So I'd like you to go through that document, and there's another video too that talks in detail about non-destructive testing, and you're going to need to look at that as well. Our first method of non-destructive testing is called it's called magnetic particle inspection. And this is actually pretty cool. What happens is you have this kind of magnet gun here that delivers a magnetic field to your part. Now the part has to be magnetic, okay? If it's not magnetic, this is not going to work. But because the part is magnetic, what happens is this spray that they put on beforehand, which is filled with small iron filings, when they turn this magnetic field, turn this magnet on, the iron filings start to align, okay? All in a straight line start to align. And then it turns out that if you have any defects or cracks or voids, then that disrupts the magnetic field, and you can see it, okay? With those iron filings, you can see the filings kind of stop and they have to go around, and that's where a crack or a void is. Now, magnetic particle inspection is only meant for a surface or just below the surface testing. It can't test for voids or cracks very deep in or deep within your product or your metal. Next is fluorescent penetrant inspection testing. And so you spray a fluorescent penetrant on an object, and then you take it under a wavelength, under a light of a certain wavelength, rather, and you can see where that dye went and penetrated the cracks of voids. In this case, they're right here. Actually, I'm pointing to here, but they're actually right here. Okay, so it's very difficult to see those before. So when you can see those, you can get an indication of, okay, how many cracks are there? Is this getting close to failure? And so that's how it's supposed to work. Then you have dye penetrance, which I mentioned to you before, is very similar, but it's not as expensive, and it's also not as precise. And what you do in this case is you clean your part, and then you essentially spray dye on it and let it sit there for a while. And if there's a crack or a defect, then the dye will go into the crack or defect. And what you do then is you'll wipe off that layer of dye and then spray on what's called a developer, which is used to pull the ink out of the crack that it went in. And so when you see blotches of ink places, you know that there is a crack that ink got pulled out of, okay? And let me not forget to tell you that the fluorescent penetrant inspection is also a surface to just subsurface as far as being able to identify any cracks or voids, okay? Now we have ultrasonic inspection, and you've heard of the word ultrasonic before. You go to the nurse or your wife or you or whoever is pregnant or has about to have children, goes to the doctor and has an ultrasound inspection. And that's because ultrasonic waves can penetrate through certain types of tissue and certain types of other things too. And so what happens is it sends an ultrasonic signal down, and that ultrasonic signal will get bounced back if it hits a void or if it hits a defect, something like that. So this one can be used for to determine if there are deep defects, okay? But it is not as difficult, not as easy to use as some of the other methods, obviously. And then here we have radiography inspection testing, which is essentially throwing some x-rays through it. And again, this can be used for recognizing deep defects and voids, cracks, whatever the case, because those x-rays go through everything else and again are bounced back when when they hit something. So you can determine where those defects are. All right, well, I hope you have enjoyed this properties of metals presentation. Thank you very much.